Góðan daginn, góðu gestir og velkomin til fyrstu innsetningarathöfnar í verkfræði og náttúruvísindasviði, á verkfræði og náttúruvísindasviði. Þetta ný athöfn, þau ykkar sem hafa starfað við erlenda háskóla þekkja til þegar þetta hefur farið fram, þetta hefð annar staðar og við viljum taka þetta upp á okkar sviði og viljum gera þessa athöfn að viðburði og tilgangurinn sá að gefa þeim sem fá framgang eða þeim sem eru ráðnir í prófessorsstöður tækifæri til þess að kynna sín stefnumál, kynna sínar rannsóknir, vekja athygli á faginu allar jarðir ef mögulegt halda svolítið upp á með þeim sem fá framgang árangurinn og svolítið hefja til vegs og virðingar aftur þetta starfsheiti prófessor sem að kannski hefur breyst og umbreyst á síðustu árum nokkuð mikið. Og að því tilefni þá hefjum við í kjölfar framgangs og ákvörðun framgangsrektors sem flytur kveðju sína hér í dag, langaði að vera með en komst því miður ekki og ég flyt kveðju rektors og hamingjóskir en í nafni rektors hafa starfsmenn háskólans fengið framgang í prófessorsstöður og fyrst til þess að halda þessa innsetningarathöfn prófessor Fjóla Jónsdóttir í vélaverkfræði. Það verður að taka það fram að Fjóla það ennþá sérstakt að kona verður prófessor í verkfræði og náttúruvísindum því miður. Þó svo að fyrsti kvennprófessor við háskólann hafi verið skipaður fyrst 1969, það Margrét Guðnadóttir og því miður verðum við ennþá að telja það sérstakt en vonandi breytist það nú hratt og án þess að gera neitt meira úr því en það líka verður tilefni til að halda upp á innsetningu prófessor Fjólu. Fjóla lauk doktorsprófi frá Brown University árið 1994 og í Mechanics of Solids and Structures. Ég mun skipta yfir í ensku núna og athöfnin mun hérni frá fara fram á ensku. The title, Professor Fjóla titles was Continue Modeling of Stress-Driven Surface Diffusion in Strained Semiconductor Materials from 1994. Before that, she finished her Master of Science in 1992 from Brown University. She finished her her bachelor degree in Science of Mechanical Engineering, summa cum laude from University of Minnesota in 1990. Her work experience before she became associate professor at the University of Iceland. She was a visiting researcher at UCSB in Santa Barbara, and she was before that a part-time teacher at the University of Iceland. She has experience from industry. She was an engineer at the engineering firm VFGK, and before that a specialist at Abacus Inc. She also served as a postdoctoral at the UCSD in San Diego and has done teaching at Brown before she finished her studies there. She has several research grants from 2001. She's been prolific in applying and run several grants and projects in her field. Lastly, in magnetorheological elastomers, and also in modeling and optimization of actuators, and several others, both from Icelandic Research Council and from other sources of grants. Her teaching and doctoral students are several, as long as master students that she has finished and has a long-standing now ilk of students that she has a network with, that some of are currently both in industry and with other universities. I personally had contact and collaboration with her in my previous job, and I recommend any company or any institute to do so. She's a dedicated member and a very well rooted in her profession, and I look forward to her lecture on research and her future, as well as some overview of her background. Fjóla, svo vel.
Thank you. Yeah, thank you, Hilmar, for the introduction, and welcome everyone, and thank you for being here today to celebrate with me. I'm going to give you a little overview of my work in solid mechanics and smart materials. I'll mention some of my work in the past and talk about some of my current projects, and a little bit about how I vision my research in the future. Well, my work is in the field of solid mechanics. Solid mechanics is concerned with stressing, deformation, and failure of materials and structures. For example, it means predicting the response of materials and structures to some type of loading, such as mechanical or thermal loading. And I have selected a few of my research projects to talk about today. Well, the story begins at Brown University in Providence, Rhode Island. It's a good place to start. I've always felt like Brown has been a source of inspiration and motivation for me throughout the years. Well, for my PhD thesis, as Hilmar mentioned earlier, I worked on what's called strained layer epitaxy. Well, typically, semiconductor devices are made by depositing thin single crystal layers of semiconductor materials on the top of a substrate. Well, if the lattice parameters of the materials do not match, we get strain in the material. Well, strained layer epitaxy has opened the door to a range of electronic products based on band structure physics. But what my work was focused on was modeling the surface diffusion due to interface misfit dislocations. And this was in the early 90s, and at the time, the role of dislocations in the relaxation of elastic strain was of great importance because of the influence that these defects can have on the performance of microelectronic devices. Well, after graduate school, there was life after graduate school, it was time to move. And Hilmar mentioned this, but I spent 1 year as a postdoc at University of California in San Diego. It was called the Institute of Mechanics and Materials. And while I was there, well, I continued my work on strained layer systems, among other things. But it was time to get a more permanent job, as for many people. So as much as I would have liked to stay in California, I ended up moving back to Providence, Rhode Island, and I started working for the company Abacus. Well, Abacus is commercial software for finite element analysis and computer-aided engineering. Well, I had done a lot of finite element modeling in graduate school, written a lot of finite element code, so this was a good fit for me. Well, although I was happy at my job, I decided in the year 1997 that it was time to move back to Iceland. And I got a job at Verkfræðistofa Guðmundar og Kristjáns, working on the design of a geothermal power plant, mostly at Nesjavellir. And then in the year 2000, I started here at the university, and well, I'm still here, and I hope to stay here for a while. So just to tell you a little bit about my work here at the university, what I've been up to. Well, there's definitely a great amount of time that we spend on teaching. So I think I've had over 1,000 individual students in different courses. My teaching has been focused on, well, mechanics, material science, mechanics of materials, finite element analysis. But besides the regular teaching, we also we mentor students. So hopefully I've given some students good advice throughout the years. I've written a lot of letters of recommendation. And then there's administration. So I was the chair of the department a few years back. I've served on a number of university and departmental committees. I've also served on committees for the Research Council of Iceland and in general, a number of services. Well, then there is research, and conducting research is kind of like starting a little company. You have to get ideas for your research. Then you have to come up with the money, so we write a lot of research proposals. And then you have to hire staff, and such as graduate students, to work with you. But research also involves for us peer review. We review research of our colleagues, attend conferences, and a number of services. Well, I very much enjoy this diversity of an academic job. But if I were to pick a favorite, I think teaching would be on the top. But I think ultimately, though, as professor, we get judged more by our research, so that's what I'm going to focus on here today. So I'm going to start by looking back a few years. Well, I had spent a lot of time at Nesjavellir when I was working at VGK at the time. So when I started here at the university, I was involved in a few projects related to this design of geothermal power plants, specifically design of steam and hot water pipes. So I'd like to start by acknowledging two of my first master students and projects that I supervised. One was by Gunnlaugur O. Ágústsson and another one by Anna Karlsdóttir. Well, moving on to very different things, I was very fortunate about 10 years ago to spend a sabbatical in University of California in Santa Barbara, very beautiful place. And when I was there, I got involved in a project on self-assembled quantum dots. Well, what are quantum dots? Basically, they are three-dimensional semiconductor nanostructure. And because of their small size, they have unique both optical and electrical properties that are different from those of the corresponding bulk material. Well, the fabrication of quantum dots typically involves large mismatch epitaxy and epitaxy of chemically dissimilar materials that results in coherent island formation. So I was able to use in this project my training and my knowledge from my PhD thesis work. Well, just quickly, our work was based on the idea that subsurface stressors, that the dot ordering is driven by the subsurface stressors, and these subsurface stressors can be buried dots themselves or misfit dislocations. So we used, for example, you see one picture here, finite element analysis to determine the stress in the vicinity of the dots and the elastic energy associated with them. Well, I had an Icelandic master student that worked with me on this, Daða Halldórsson. And just quickly, another project that I worked on while I was at UCSB, it was modeling of threshold strength in ceramic composites. Well, the major drawback of ceramics as structural components is their brittleness. And brittle materials are known to contain a variety of flaws and cracks. So you see here the failure strength versus, the flaw size or the square root of the initial flaw size. So we have a monolith and we have a laminate. A laminate is just layered material, whereas a monolith is just a bulk of material. So you see that the laminate has what we call a threshold strength. So below that value, there's no possibility of failure. So our idea was to increase the damage tolerance of ceramics by using compressive layers to arrest the cracks in the tensile layers. So my job was to model this numerically and using the principles of fraction mechanics and compare this to experimental data. And all the experiments were carried out at UCSB. Well, I wanted to mention these two projects as an example of the importance of sabbaticals, because I wouldn't have gotten involved in these projects at the time if I hadn't been at UCSB. Well, then on to more of my recent work. Well, a few years back, as Hilmir mentioned, I started collaborating with the company Össur. Well, Össur uses smart materials in their products, such as magnetorheological fluids. And when we say smart materials, we mean materials that can significantly change their properties by, in a controlled fashion by some external stimuli, which could be stress, could be temperature, can be electric or magnetic field, as in this case. And these materials are often used in sensors or actuators. So I've listed here 4 projects that I worked on, along with a number of my students. Optimization of a magnetorheological fluid brake in a prosthetic knee, MR fluids design, durability of MR fluids, and then finally MR elastomers. So let me tell you a little bit more about these smart materials. Well, MR fluids, they change their rheological properties, or they can be controlled by the application of a magnetic field. So normally we have micron-sized iron particles suspended in a carrier fluid, so we have some type of oil as the base fluid. And then under the influence of a magnetic field, the particles, you see them there as randomly distributed. So when we apply a magnetic field, the particles become aligned in the direction of the magnetic field, and hence restrict the movement of the fluid. So the fluid increases its viscosity. And so the fluid basically changes from being oil to being more like peanut butter. And here you see a picture of, this is an SEM of the actual particles that are used in the Rioni by Össur. They have a mean diameter of about 2 microns or so. So tell you a little bit about the MR fluid brake. Well, an MR fluid brake, it's a device that transmits torque by the shear force of the MR fluid, and the braking torque, it changes quickly in response to an external magnetic field. So that means that for the user, the stiffness of the knee can vary in real time. And we saw in the previous slide, you saw that, well, under the influence of a magnetic field, the viscosity of the fluid is high, and this is what defines what we call the field-induced or on-state braking torque. And we want to maximize this value for more demanding tasks for the user. Well, in the absence of a magnetic field, we saw that the viscosity of the fluid is low. And this defines the off-state torque or the stiffness of the knee, and we want to minimize this value for user comfort. We also think about the weight. So our work was then focused on finding the optimal design of the magnetic circuit in the knee, and also we looked at the quality of the fluid. So we were seeking sort of the best combination, we say like a suitable balance between the strength, the off-state viscosity, and sedimentation stability. Well, this is the component that we're focusing on, and here you see a schematic layout of the magnetic circuit. We have a core. Well, this is, I should say, it's an axisymmetric view, and you see there the rotation axis of the knee. We have a core which is made of cobalt iron, and cobalt iron has a very high magnetic saturation value. And then you have the coil wrapped around the core. Well, the arrows show the direction of the magnetic flux, and here you have the steel plates and the MR fluid between the blades. So as the knee rotates into flexion or extension, the steel plates shear the particle chains to create resistance. The gap between the plates is very small, only about 20 microns. So if you think of the particles you saw earlier, there are 2 microns, you can have about 10 particles to fit in each chain. Okay, a few equations. Well, I stated earlier that the braking torque is derived by the shear force of the MR fluid. Well, in the absence of a magnetic field, an MR fluid behaves just like Newtonian fluid, just like water. But in an active state, it can be characterized by the Bingham model. The Bingham model gives us the total shear stress by this equation here. You have the what we call the shear yield stress, and that's a function of the magnetic flux density. We have the plastic viscosity, and you have the shear rate. And then from this equation, we can derive an equation that gives us the braking torque in the knee. It's this equation here. So you see here the shear yield stress, and this figure shows us the shear yield stress as a function of the magnetic flux density. So as I increase the magnetic flux density, I increase the shear yield stress, and in return I get a higher braking torque in the knee. This part is the viscous part. You always have some, what I call the off-state stiffness earlier. So we want to maximize this whole value. There are a number of other parameters, of course, that come into play that I'll mention a little bit later. Well, how do we determine the magnetic flux density? We can do that by using a finite element analysis. And here you see a 2-dimensional axisymmetric view. Here you have the core, which is made of cobalt iron. So the red color here means that the core is saturated. The magnetic flux lines go like this into the fluid. This is, if you look at this one here, this is where you have the fluid and the steel plates. So you want to maximize the value in the fluid. But according to this picture and this design, we are getting an average of about 0.6 Tesla. Well, once we have optimized the magnetic circuit, we also wanted to look at the rheological properties of the fluid. Well, it's well known that the rheology is affected by particle size distribution, and volume fraction of solids. Probably the most obvious way to increase the strength would just be to pour more particles into the fluid. But at the same time, then you increase that off-state viscosity that I talked about. So here you see a picture of my former PhD student that worked very hard on this, Ketill Heiðar Guðmundsson. Well, what he did, he made a number of fluid samples with different grades of particles and different compositions, and measured them all with this equipment here, a rheometer. And these measurements were carried out at the Leibniz Institute for Solid State and Material Research in Dresden, Germany, simply because we don't own this equipment and we don't have it in Iceland. So just to show you one example, he did a number of examples. Here's just the result of one such example. You have the off-state viscosity. Here you have the carrier fluid. Here you have the MR fluid. You see that the MR fluid has about 3 times the viscosity of the base oil. We're only concerned with high shear rate, so we're not concerned with this part here. And then here on the right, you see the flow curves in an active state. And this is the shear stress versus the shear rate for an increasing value of magnetic flux density. Then you have to think back. We use the Bingham model that I showed you earlier and take that value right here, and that gives us that shear yield stress. So we can plot that as a function of the magnetic flux density. And we want the higher value of B. I said earlier that the average value is about 0.6 Tesla in the fluid. So what Kenneth did also this was part of his PhD thesis work, was he took all these different parameters in that equation and also these parameters in the fluid and optimized them, and this is the result. So for an off-state stiffness of about 2.4 Newton meters, which is acceptable by a user, you can get a breaking torque of 60 Newton meters. I would also acknowledge other students that worked with me on this through the years, such as Sigurður Gísli Karlsson and Eggert Þröstur Þórarinsson. Well, a little more about MR fluids, but another project that was a master's project by my student Einar Hreinsson, and he finished this in 2011. He is now an employee of USSR. So after long periods of usage, the MR fluid brake becomes stiff in off-state mode and eventually needs to be replaced. So what Einar did was he analyzed the morphology, the size distribution, the chemical composition, and magnetic characteristics of a used fluid and compared it to new fluid. So what you see here new particles compared to particles that have been in the knee for about 2 years. Well, the results indicate that small particles have peeled off the skin and peeled away from the surface, which causes thickening of the fluid and then in return causes stiffness of the knee. This is ongoing work, and we are in collaboration with USSR and Professor of Chemistry, Professor Bombard in Brazil. So we're looking at different combinations of fluids and see if we can increase the durability. Okay, I've probably said enough about MR fluids, but another project that, well, having spent all this time on MR fluids, it was kind of natural to work on solids. So the solid analogs of MR fluids are what we call magnetorheological elastomers. So the difference is that instead of having oil and particles, now you just take an elastomer or rubber-like solid and put the particles in there. So you saw earlier that the fluids have a controllable shear yield stress, while then the elastomers have a controllable stiffness. So what you see here you see an elastomer where, these are a random distribution of particles. Here on the right, you see the particles aligned in a chain, which is stronger or gives a higher stiffness. Well, these MREs, they have many potential applications, such as in shock absorbers, prosthetic devices, actuators, but we still don't have them, though, in many commercially available products. So what we are interested in is to use this in a variable stiffness foot by USSR. Here you see a carbon fiber foot. And, well, the stiffness of the foot and its response can be controlled by the thickness profile of the foot, but you still have a fixed stiffness. So the idea here is that the user can change the stiffness according to the activity level. So you want to maybe different stiffness if you're running for the bus or dancing or whatever you're doing. I've already had one master student that worked on this, Ívar Guðmundsson, and he finished in 2011. Here he made this sample, which is silicon-based. And as I said, this is ongoing work. And according to the literature, the MREs can increase their stiffness considerably, but these results vary depending on the materials used, the methods used. So we have to try this for ourselves. And the challenge is, we know that we can make this samples and make them work, but the challenge will be if we can get a high enough MR effect. And by that I mean if we can get a high enough change in stiffness for it to be usable in a commercial product. But I'm hopeful and excited about this project, and I have another master's student that's working on this right now. Well, finally, a project related to this, not MR though, and I would like to mention is cross-disciplinary work between myself in mechanical engineering, Sveinn Páll Sigurðsson in computer science, and Már Másson and Bergþóra S. Snorradóttir in the Faculty of Pharmaceutical Sciences. And this is also in collaboration with USR. So what we are working on silicon-based drug delivery system. I call this my drug problem. So, well, our motivation is that medical devices that release drugs or some other bioactive compounds are of interest for a variety of applications. Here you see, for example, a silicone liner that's made by USR. And silicone is commonly used in various types of devices. So we can embed drug into in the polymer and then release the drug in vivo. For example, anti-inflammatory medication like ibuprofen. So our objective is to develop a numerical model that describes the controlled release of drugs from silicon matrices, and then we compare this to experimental work. Well, our numerical model is based on two coupled nonlinear partial differential equations that we solve. Here you see these, a schematic of these matrices with 5% ibuprofen in each layer. So we're looking at these as layered matrices. So then when we solve these equations and we calculate the amount, so calculate the amount of drug that's released out of the matrix. And here you see one example of our calculations. This is the quantity of ibuprofen released versus time, 400 days. And this is a comparison then with experimental data that's been collected at the Faculty of Pharmaceutical Sciences for 400 days. And those are the dots, and our numerical results are the solid lines. So this compares fairly well. And we've done this for simpler geometries. I've already had one student work on this that I wanted to acknowledge, Ruth Guðmundsdóttir. She finished her master thesis in 2011. So this is also ongoing work. Well, future directions, I've already mentioned a number of these projects that I'm working on. But just to reiterate, well, I want to continue working on this numerical model for controlled release of drugs. So we're extending the model to include some more complicated issue, such as inhomogeneous drug dispersion. We also, if we want to use this in a medical device, we have to account for more complex geometry than we have for now. So this is ongoing. Another thing, I also would like to continue my work in smart materials. I've talked a lot about material MRFs and MREs, and we can also think of this as magnetorheological gels. So, as I mentioned, we're currently working on the magnetorheological elastomer for use in prosthetic devices. That means both fabrication of the material, mechanical testing, and numerical modeling. But all of these have many other applications, such as in sensors, actuators, and many medical applications. So when I think of them, they're basically devices that mimic biological systems. You can think of even the human body as being the ultimate smart system. But another area that I've currently become interested in and really hope to do some work in the future is in biomaterials or biomechanics. For example, I'm currently looking at what are biomembranes and ways to model them. Well, biomembranes are just cell membranes that form the boundaries of living cells. I don't know anything about biology. Well, not much. But what I'm planning to do then is to use my training in mechanics to model the deformation. And from a mechanics point of view, the structure of a biomembrane is interesting because it's quite different from the classical structural membrane. So I teach my students in mechanics that a membrane usually means no bending resistance. Just think of you take a piece of paper and you can bend it easily, but it's difficult to stretch. But in biophysics, a membrane means elastic bending resistance, but what we call no in-plane shear stress. So normally then in these commercial packages, we have shell elements that are used based on the structural shells. So this will be a challenge to do this, but I'm hoping to do what I call a continuum-based model. Well, that concludes my overview. So I just want to thank all my collaborators, my colleagues, and of course all my students that I've had, both undergrad and graduate students. And thank you for your attention. Thanks.
Now, this is the last time we can put Fjóla on the spot.
Okay.
I think if I may start, some of
Okay.
this is very relevant to my previous life, but I'm more interested in the future. And I'm wondering, you worked on the edge between companies and research, and the small and the macroscopic properties. Are you on your biomechanics and your films? Do you see similar trends or similar applications, or like you've seen in the others?
Yeah, I think, as I mentioned, I mean, maybe it looks like I'm jumping around working on different things, but there are definitely connections between them. And while having worked with them in pharmaceutical sciences, they have films of silicon. We're doing modeling of that. The other project that I mentioned, it's required different things, but I think working on the other one got me interested in this one.
Perfect. More questions? Open for questions to Fjóla from anyone. Biofilms, or the future. I see definitely a trend in your research in the future, and I look forward to see come out of it. Any more?
Difficult questions?
Yeah, last opportunity. If not, then I think I would like to ask you to write your names in the book for inaugurations that is just outside. Það er bók með svona gestabók. Við ætlum að bjóða til, Fjóla ætlar að bjóða til samfagnaðar hérna fyrir utan, þar sem að hægt er að spurja. Ég þakka ykkur kærlega fyrir þáttökuna og hérna til hamingju, Fjóla.
Já,
og ég vona að þetta verði viðvarandi og oft sem við fáum að þess notið að fagna framgangi fólks að þínu kaliberi í prófessorstöðu. Takk ykkur fyrir komuna og njótum þessum eftir dagsins. Takk.